Alright, in section 5.6, we're talking about rational functions. So a rational function is a function that can be written as a quotient, or basically a fraction of two polynomials. And we'll call those polynomials p of x and q of x. So f of x, if it's a rational function, it will have a polynomial in the numerator and a polynomial in the denominator. But the polynomial in the denominator cannot be equal to 0. Otherwise, you will have something that would be undefined. Remember, 0 over a number, that's 0. Whereas a number over 0, hey, that's undefined. Okay, so let's look at something called a vertical asymptote. Alright, a vertical asymptote of a graph is a vertical line x equals some number, where the graph tends towards positive or negative infinity as the inputs approach a. So basically, x is going to go towards this a value regardless, and it doesn't really matter what y does. It can go to infinity and negative infinity. Kind of like this right here. So we've got a vertical asymptote right here at x equal to, looks like 4. Okay, so there, the dotted line right there, that is my vertical asymptote. And notice that the graph over here is getting closer and closer to x equals 4. The graph over here is getting closer and closer to x equals 4. Whereas the y values, as they're going up, they're going to positive infinity. As they're going down here, they're going to negative infinity. So the x values are getting closer and closer to this 4. The y values are going positive and negative infinity for this case. Now over here we've got another one right here. This one is at x is equal to negative 4. Same thing, this graph is getting closer and closer to 4. Or sorry, negative 4, and this graph over here is getting closer and closer to negative 4. Now it will not ever be negative 4, and it will never cross that asymptote. It just gets really, really, really close to it. Now horizontal asymptote is a graph with a line y equals some number, where the graph approaches a line as the inputs increase or decrease without bound. So x can be approaching positive or negative infinity, it doesn't matter, but y is going to approach that b value. So if we look at this right here, so this is y is equal to, looks like 1. Now notice how this direction your function is getting closer and closer to 1. This direction your function is getting closer and closer to 1. Now for the x values, this is negative infinity. Over here, this is positive infinity for your x values. So your x values can kind of go wherever, but your y values are getting closer and closer to y equals 1. And same thing over here, this is y is equal to negative 5. So this function, and let me erase some of this. This function right here is getting closer and closer to that asymptote, but it's never going to touch it, never going to cross it. Same thing over here. Gets closer and closer to that asymptote. So all the y values are getting closer to negative 5, and your x values are kind of going everywhere. Over here it's negative infinity for the x values. Over here it's positive infinity for your x values. Alright, and that's for your horizontal asymptote. So let's look at this one and identify if we have any horizontal or vertical asymptotes. So it looks like I've got this one right here, this first dotted line, that's our first asymptote. That looks like it's x is equal to negative 2. Okay, now this vertical asymptote looks like it is y is equal to 3. Okay, so we have a vertical asymptote of x equals negative 2 and a horizontal asymptote of y is equal to 3. Okay, let's look at this one. Okay, so this first asymptote, that looks like that is x is equal to 1. The second asymptote, that looks like that is y is equal to negative 7. So our vertical asymptote is x is equal to 1, and our horizontal asymptote is y is equal to -7. Okay, now let's look at the domain of a rational function. So the domain of a rational function includes all real numbers except those that cause the denominator to be 0. And that's what we were talking about when we were looking at this right here. And we said that, hey, q of x cannot be 0 because then I would have some number divided by 0 and that will be undefined. So whatever makes this polynomial 0, we have to exclude from the domain of the rational function. So let's look at this right here. Find the domain of x plus 3 over x squared minus 9. I'm not worried about the numerator. I'm worried about the denominator. So I'm going to set it equal to the thing that I don't want it to be. Or you can say, okay, hey, can't be equal to 0. That's fine too. So we're going to move 9 over, square root it, put the plus or minus sign there. So plus or minus 3. Okay, so your domain can be anything except positive 3 or negative 3. So we can start at negative infinity and go all the way up to negative 3, union that with negative 3 and everywhere in between negative 3 and 3, union that with, okay, starting back at 3 but not including it, and going all the way to positive infinity. So this would be my domain right here. Okay. Now here's a graph of this function right here, what we just found. Now what we're going to see is, and let me write it up here. Notice we have an asymptote at x equals 3, so the graph is not even touching the x equals 3, so that's why, because it's going to be 0 on the denominator, so it's undefined at that point. But this graph doesn't show it. You're going to have a hole right here at x equals -3. So that graph will come up, come up, come up, come up, come up, skip over, and then go back. Okay, so we'll have a hole there. Now, how do you figure out, am I going to have an asymptote or am I going to have a hole in my graph? Is we're going to look at this function right here, and I'm going to factor out the bottom. So x plus 3. Now we can write x squared minus 9 as 3 squared. And hey, that's the same thing as a squared minus b squared. So that will be a minus b, a plus b. So for this will be x minus 3, x plus 3. So x minus 3, x plus 3. Now notice if I can cancel out the top and the bottom, so this was one of my problem points, and if I can cancel that out, that means that I'm going to have a hole in my graph. But if I can not cancel out the problem pole, that means that I'm going to have an asymptote in my graph like I do here. So notice if I take x minus 3 and I set it equal to 0, hey, that gives me x equals 3, which we already see in the graph that we have an asymptote at x equals 3. But if I take this right here, x plus 3, and set it equal to 0 and solve, hey, at x equals -3, I've got a hole, which lines up because I was able to cancel that point out. So that's how you can tell if you've got a hole in your graph or if you've got an asymptote in your graph. Okay, so identifying vertical asymptotes of rational functions. Okay, so we're going to factor the numerator and denominator. We're going to note any restrictions in the domain, reduce the expression by canceling common factors in the numerator and denominator if we can. Note any values that cause the numerator to be 0 in this simplified version. These are where the vertical asymptotes occur. After you start canceling out factors, if you have factors that you can't cancel out, hey, those are going to be asymptotes. Note any restrictions in the domain where asymptotes do not occur. these are removable discontinuities or holes. Okay, so let's look at this one. So we're going to find the vertical asymptotes, and we're not going to be given a graph, so we're going to look at this right here. So the first thing I'm going to do is I'm going to factor the top and the bottom, and I'm going to change that to where it's in descending order. And the next what I'm going to do is I'm going to get rid of this negative, kind of pull it out. So x squared plus x minus 2. Okay. Now I'm going to factor the bottom. Doesn't look like I can factor the top. Okay, so I'm going to try to factor the bottom here. So an x and an x, 2 and 1. So negative 1, positive 2. So negative 1 times 2, that would give me negative 2. 2 minus 1, that gives me positive 1. Okay. So it doesn't look like I'm able to cancel anything out. So it looks like we're going to have some asymptotes and we're not going to have any holes. Okay, so we're going to take negative x minus 1 and x plus 2 and set that equal to what we don't want it to be. Now I can go ahead and divide both sides by the negative 1 just to get rid of it. Okay, so then what we do is we separate it out. So x cannot equal 1, x cannot equal negative 2. Okay, so we can go from, well, they're not asking for the domain, so we don't need to write that. So what we have is an asymptote at x equals 1 and x equals negative 2 for this particular graph right here. So there's our vertical asymptotes. All right, taking a look at the graph of that function, it looks like that we do have an asymptote at negative 2, and we do have an asymptote at x equals 1. So we did find the correct asymptotes for that function. Okay, now a removable discontinuity of rational functions, that occurs in the graph at x equals a if a is a 0 for a factor in the denominator that is common with a factor in the numerator. Meaning, if you can cancel out that factor, then hey, you've got a removable discontinuity, which is a really fancy way of saying, hey, you've got a hole there. So when you factor the numerator and denominator and check for common factors, if you have any, then we set the common factor equal to 0 and solve. This is the location of the removable discontinuity, or the hole. Okay, so here, let's look at this one, and we're going to factor the top, can't factor that one, and the bottom. And again, we've got x squared minus 4, which we can write 2 squared. So that's a squared minus b squared, or a minus b, a plus b. So that means that this will be x minus 2x plus 2. So x minus 2x plus 2. And hey, look, we can cancel out the x minus 2. So I'm going to set the bottom equal to 0. We'll go ahead and set the whole thing. Or not equal to 0. So x minus 2 not equal to 0 and x plus 2 not equal to 0. So x equals 2 and x equals negative 2. So at this spot right here, that was this one right here, we have a hole in our graph. At this spot right here, that was this one. Since we couldn't cancel it out, that means that we have a vertical asymptote at x equals 2. So what we can say is, if we get rid of all of this over here, we have a vertical asymptote at x equals negative 2, but we have a hole at x equals 2.